Okay, let's have a look at a few more examples. Here's the first one. Limit as x tends to 0, sine x over x. That's a very popular one. Right. Well, if you take a look at this, it's the form 0 over 0. So if you differentiate the top and differentiate the bottom, you get cos x over 1. Look at that. As it tends to 0, it's 1. So there's your answer. Right, here's the next one. X squared minus 1 over sine of x minus 1. Okay, so if x is 1, that's going to be 0, and if you put x is 1 in there, it's going to be 0 as well. So it's another one of the forms 0 over 0. And if we then differentiate the top, you get 2x. And if you differentiate the bottom, you're going to get cos of x minus 1. If you put x equals 1 in there, you'll get 1 minus 1 is 0. So that'll be cos of 0 is 1, and you put x equal to 1 there, and you'll get 2. So that's quite easy. All these look very easy at the moment. We look at this one, it gets a bit more difficult though. The limit is x equal to 0 of this lot. Well, if you put x is 0, we get 0 minus 0 there, and sine of 0 is 0, and you're going to get 0 from that as well. So you get 0 minus 0 over 0 minus 0, and that's the form 0 over 0. And so we could try differentiating it, and if you do that, you get 2 cos x and 2 cos of 2x, with a minus in there, and that's going to be 1 minus cos x. After you substitute x equal 0 into that, though, you get that's again of the form 0 over 0, so it's again indeterminate. So if you want to find that limit, of course there's no reason why you shouldn't do it again. And if you do it again, you get this time cos goes to minus sine when you differentiate, so you get minus 2 sine x plus you get another 1 coming out of there, so it's minus, so that comes a plus, so it's plus 4 sine of 2x over, and if you differentiate minus cos, you get sine. And if you try that when try setting x equal to 0 there, again you get a 0 at the bottom, and at the top you also get 0. So it's again of the form 0 over 0. So if we try it yet again, you get finally you get if we differentiate that sine x, you're going to get a cos x down here, and of course when you set that to 0, it's going to be 1. So we might get out of the woods at this point. And sure enough we do, because if you differentiate sine x, you're going to get cos there, so it's minus 2 cos x, and you're going to get another 2 coming out from there to make it 8 cos of 2x. And now when you set x to 0, we get something sensible out, because cos x of course is going to be 1, and so you get minus 2 plus 8, which is 6. So here's your answer. So that limit is therefore 6, and so that limit is 6, and so is that one, and therefore so is that one. And let's have a look at this. N is some integer constant here, greater than greater than 0, no, greater than 1 I should say. Some integer greater than 1. And if we're looking at what that is, of course if you differentiate the top now, you're going to get n x to the n minus 1, as you might expect, and if you differentiate the bottom of e to the x, you'll still be left with e to the x. And you can carry on doing this again, and you'll get n into n minus 1, into n minus 2, and so on, and right the way down. If you just keep repeating this process, you end up with factorial n on the top and e to the x underneath, and you're asking for the limit as that goes to infinity, and so the answer is going to be 0. And that's quite important because it tells you something. It tells you that that limit is 0, so what that means is that x is going to infinity faster than any power of x. Okay, so we got x equal to 100 or something, in n equal to 100, say, in there. So x to the power 100, we said x to infinity. Okay, that starts to climb up fairly rapidly, but e to the x might start off below it, but eventually it's going to overtake it, and it will go to infinity faster than any power of x. And that's quite an important point. Okay, right, let's sort of look at here at something where L'Hopital's rule is not a good idea. Because if you look at this, you might be able to differentiate the top, and that's fine, but if you try differentiating this lot, you'll just end up with a most horrible mess. So this is a case where you want to use a bit of intelligence here. And if you substitute x equals 3 into this thing, you'll get 0 over, well, it turns out to be 1 minus 1, which is going to be 0. Okay, so you get a 0 over 0. So we got to think for a bit, and what you want to do really is to get rid of these square roots underneath. Okay, and you've got something like the form a minus b, right? Now if we could square, so we had a squared minus b squared, we'd have got rid of those square roots. And indeed that's what you can do if you think about it. If you multiply the top and bottom by this expression, okay, you've got something like a minus b here, and this is like a plus b, so that'll give you a squared minus b squared, which nicely gets rid of those square roots. So if we do that, you'll get that underneath and that on top. And we can ask, well, what is this thing underneath? Well, that's we got 2x there minus 6. And if you look at this up here and that down there, those two expressions, you'll see that one is twice the other. So you could divide the top by x minus 3 and the bottom by x minus 3, and you get 2 underneath. And now if you look, see what you get when you say x equals 3 in this expression here. You get 3 minus 2 is 1, plus 4 minus 3 is 1, so that's 1 plus 1. You're going to end up with, when you take square roots, which is 2 divided by 2, so the answer is 1. So that's the limit. And there's an example where you have to use a bit of algebra to get the limit. It's probably better to do that than to attempt to use L'Hopital's rule, which will end you up in a most appalling mess when you try and differentiate the bottom there.